It's my pleasure to welcome Jason Shankel, that is gracious enough to come here every semester. We truly appreciate Jason. He brings so many different topics to us, talks about so many different topics. Welcome, Jason Shankel. Thank you for coming.
My name is Jason Shankel. I am a senior gameplay engineer at a company called Fable Labs. We do story-based games for mobility and web. But I spent a good portion of last year working with a number of partners on some VR technologies. And I'm here today to talk to you a little bit about the technological considerations for rendering in VR. First, let me get a little the survey here. How many people have done any graphics programming or are familiar with basic graphics? Okay, cool. Experienced VR? Are they on a phone or with an Oculus or anything like that? Put a rig on your head? Okay, a little bit. So good. So just want to get a sense of experience level. Okay. So the first thing to talk about is, the VR market forecast going forward. This is data from mid-2014, so I should probably update it. But as we see here, we have this. We're now, coming into here and seeing this rise of VR systems. Back at this point, we were talking about mainly about Oculus and a few interesting things from Samsung that might work or not. And now we're seeing the first round of consumer level systems coming out. And the projected growth of the market from BI Intelligence, goes this way. And so whenever we see graphs like this in technology, we get very excited because here there'd be money, right? Here there'd be money. So before I get into the tech and the sociology of it, I should give you a little bit of my own perspective on where we are and where we're going here. I am a bit of a VR skeptic. I think that it's a very interesting technology. It's very compelling. I've done it and working with it. I think it's great and it's really a game-changing type of thing. But I think it has some fundamental issues, especially around being socially isolating. It's sort of the anti-we. Putting a box on your face and locking yourself out from the people in your immediate environment is going. I think that there's fundamentally very little way of getting around that, and so I think it's a type of technology that's going to find a niche. But that doesn't mean it's not compelling. It's not interesting. Another niche technology is a Bluetooth earpiece for your phone. Very few people. These were very popular for a long time. Very few people have them now, but the people who have them really use them. People who spend their life on the phone, salespeople, and that kind of thing. And the technology in that area has ballooned out of control because of this concentrated niche market. So where I think we'll probably go through a phase like we did with Wii, where people got really excited and had a lot of fun and people were gaming who were never gamed before, it also has the potential of there being a fad level to it and it's sort of leveling off. But that doesn't mean it's not an interesting technical problem. That doesn't mean it's not going to be an exciting part of the industry going forward. And it also doesn't mean I'm right. I've been wrong about this kind of thing about half the time. So, grain of salt. I also want to point you to some of the talks that inspired this talk. I'm standing a little bit on the shoulders of giants. I spent, like I said, about half of last year really delving into this stuff, but not all the way down to the gears and the metal and that kind of thing. Just working on a few projects. For a couple of incubators. So I can't recommend highly enough John Carmack's Oculus Game Developer Conference keynote address from last year. This is the guy, who knows who John Carmack is? Okay. John Carmack is the developer of Doom and Quake. He put together id Software along with Michael Abrash and a few other people. And he basically created, if you play video games, who plays video games? All right, you guys, this is the guy who did it for you. Right, these two is created this world where now you can just download the Unreal Engine, build your own maze, run around in it. But back in the days, John Carmack, that created the world that we're in. And he gave a great talk about where he sees virtual reality taking the experience that he's spent 25 years building. How it's going, this is like his dream technology. This is what he was talking about in the 90s. And so it's a very sort of visionary, forward-looking idea of what consumer products are going to be like, what kind of arts we can produce, what kind of products we can make, and basically lays out a very good vision for that, where we can go. At the bottom here, Michael Abrash, Anybody know Michael Abrash? Michael Abrash? Okay. Michael Abrash is the god of graphics programming. He wrote the black art of graphics programming. He developed the Quake engine at id. I was fortunate enough to be in his, I think it was 1995 GDC talk where he described the layout of the Quake engine, and we were a bunch of, game developers who'd been doing sprites and Pac-Man, in the mid-90s up to that point, and it just completely blew our minds how they, were doing spatial partitioning and how do you reduce 1,000,000 polygons to 1,000 polygons and how do you rasterize them on the screen and all stuff that you don't even have to worry about anymore because you can just download CryEngine or Unity or Unreal and just, who cares how it's built, right? Well, he's the guy who laid the technical foundation where Carmack did a lot of the design foundation for what we have today. And and he gave a very interesting talk on how VR will affect us personally, and how as gamers and will it really matter to you? Or will you just go back to your couch? And so he can't recommend Michael Abrash highly enough if you're interested in graphics development. Most of this talk, however, is based on the work of Alex of Lacrosse at Valve. This is where I pretty much took my lessons throughout the year. Valve and NVIDIA are the ones who are way out ahead on this stuff. This talk is based very directly on advanced VR rendering, which is also a GDC 2015, talking about all the technological considerations for what you have to do to render. It's a word of warning. It assumes you already know everything you need to know about rendering for a regular screen. It's highly technical. So you might need some, if you're not incredibly familiar with pipelining and all these other and texture bandwidth and things like that, you might get a little bit lost in it. I've tried to make this talk a little bit more of a primer, but if you do have a little bit of background on this is amazing stuff. That's why I'm talking about it today. Okay, so what do you have to do to the rest of these slides are the things that you have to do in order to make VR succeed. Okay. And the first thing you have to do is you have to embrace the past, right? And Carmack and Abrash represent the past with Quake. You have to know how to organize a world in geometry so that it can be rendered from the point of view of a camera. All right, and we've done a ton of work on this over the years to the point now where if you're playing video games or you're interested in writing one and you're downloading an engine on the thing, you're not even thinking about it. It's just the language that we already have. Okay, so we have to recognize that when I started in this industry, like 25 years ago and then like 20 years ago when 3D really started to take off, none of this was intuitive. None of this was stuff that we all just knew how to do. Okay, it's very advanced geometry. It's very advanced, highly efficient, looking for every order log n way that you can navigate a world type of stuff. And there is a ton of established material that has gotten us to this point where we have Call of Duty and Skyrim and that kind of thing. And that is the vast bulk of what is going to be going on in any VR system, is that stuff that's already built. Okay, we can't throw it all out. We can't go and start from the beginning and say we're going to do a ray casting system or some other kind of thing without losing a lot of time. So we're going to be basing everything that we do on the 20 years of experience that we've got developing games now that practically look like reality and movies. Okay, that's our foundation. But you've also got to erase the past. I like to sort of think of virtual reality technology on what I call the Keanu scale. At the low end of the Keanu scale, you have Johnny Mnemonic, right from the 90s. You have the Virtual Boy, you have the Cybermax, you have the Nintendo Power Glove, you have all this kind of thing that we're doing where this was basically a science fiction technology. When I was coming into the industry in the mid-90s, this was something you'd see in the movies, you read about in books, and we had some basic demo technologies that kind of gave you the idea, but they all sucked. They all stank. Nobody ever really did this for more than just, some shits and giggles. It was never compelling. Okay, why? Fundamentally, you all have something in this room that's very, very valuable to those of us who are game developers, filmmakers, television producers, people who communicate with you using a screen. Okay, you have an imagination. an imagination barrier. So that when you're sitting in a movie, even a 3D movie, okay, or you're playing a video game, your body does not think that you're in another world. You don't think that you're going to be blasted out into space when you watch Star Wars. You know, you don't think that you're in World War II when you watch Saving Private Ryan. Okay, because you understand that you're viewing a window with action that's moving around in it that has nothing to do with you being physically present there. And you can enjoy it, and you'll accept a lot of flaws. You know, I do filmmaking as well, and in filmmaking we say that sound is the most important part of a film. The image is not as, it's important, but it's not as important. Because you cannot filter sound. You can't shut your ears, and sound either convinces you it's real or it doesn't. Where an image, audiences will forgive bad images. You know, we expect cheesy effects and things to not look completely real because we understand that we're seeing a representation of reality and not real reality. Okay, so we have an imagination barrier between our eyes and our brain that does not exist between our ears and our brain. Right? And these technologies pretty much slammed directly into the imagination barrier without realizing they were going to do it. Because the problem they were trying to solve back then was pretty much, okay, we have Doom and Quake and these couple of, you know, especially space games in 3D were pretty performant back then. So it's like, all we got to do is take your monitor, stick it on your face, and you'll feel like you're in the world. And that turns out to not be true. Because it wasn't tracking your head movement, because you didn't feel like you were in a real 3D sensorium, because it really felt like all that had happened was a video screen had been jammed into your face. And once it was jammed into your face, then your imagination barrier gets weakened, and it says, I can't quite interpret this correctly, but it doesn't seem real, and so you're going to get sick. Your body's going to reject what you're being asked to look at. Okay. Modern VR technology, even the most basic stuff, that doesn't have very good graphics yet. You know, we can't really afford the highest quality graphics on VR because we have to do so much extra work to make it happen. It's very compelling because as you move your head, the world you to the left, you see things that are to your left, and that right there breaks down the imagination barrier completely. It no longer feels like this is wrong. It feels like it's okay, especially with higher scan rates and everything else. Even though you can tell you're not in real reality, your body accepts it as real reality. And that's the fundamental difference what we have to erase about the past, which is that we have to realize that this isn't just a new kind of monitor and joystick. Didn't just turn your head into a joystick. We are taking you into a completely different kind of experience than what you have with a 3D game. We're taking you from experiencing a serialized image that's distant from you, that your mind understands is not where you are, to something that really is fooling you on a limbic level. Okay, so that even though if your mind knows you're not in a reality, your brain doesn't. Okay, and that's a completely different kind of thing, and we didn't appreciate that back then, and they made terrible technology as a result. Okay, so what does this mean? This imagination barrier being in the way. Okay, it means that we have to provide direct verisimilitude to your brain that satisfies your expectations of a real environment, not that it satisfies your expectations of film. There's an old apocryphal story about the Lumiere brothers when they showed their first motion picture. It was a train coming into a station. It was the first official motion picture that people paid to see. And they say that people panicked because they thought a real train was coming into the station and was going to knock them down. Right? Well, that's not exactly true. I mean, they knew, they weren't, farm animals. They understood that they had paid to see a light illusion, and there's no train tracks around here, and there was no sound, and there were all nobody was actually fooled. But they had that immediate visceral reaction because they were not a generation of people who were used to experiencing life through a screen. So it was it's like a roller coaster. It panicked them a little bit. Okay, we all are beneficiaries of a century of everybody growing up with TV and movies and video games to the point where we understand a screen, and we might have that reaction if the music is just right and if it's really heavy and if it's hardcore Henry or whatever. But we're very muted in our responses to those things, right? Similarly with VR, I think that we're going to be meeting in the middle as we get used to using it. If it becomes a bigger technology than I think it will, but if it gets, then down the road, the generations that are using it will be used to some of the flaws in the verisimilitude of the system. And we're going to be coming back this way to make those flaws less and less apparent. And the first thing is you got to draw everything twice. Right. So the old VR systems, the ones that failed pretty badly, they just showed you like Doom, but they showed it to you as a flat image rendered from one camera point of view and projected into both eyes. No depth perception at all. Your body wants depth perception if you have it. Now, if you only have one eye, or if you have a lazy eye and you don't have depth perception, it might not be much of a problem for you, but for the bulk of the audience, anybody who can appreciate a 3D film, when you put these goggles on, you need to have depth. And in order to have depth, you have to draw things from the point of view of each eye and draw 2 full images that get rendered, into the goggles. The problem with this is that, we don't naively just draw everything in a world, right? We have a point of view of a viewer, okay, is a frustum. It's a matrix that describes your position, your orientation space. We project this frustum out. We gather all of the geometry that intersects that frustum, and we draw it, okay? And we don't just draw it back to front or in whatever order we want. We draw it based on material, right? So, like if I'm going to render this room, I'm going to load up the materials for the ceiling, and I'm going to draw all of the whole ceiling. Then I'm going to load up the material for the floor. I'm going to draw the whole floor. I'm going to load up the material for a desk. I'm going to draw all the desks. I'm going to load up the material for the wall. I'm going to draw all the walls. The reason for this is that the traffic that it takes to send your material to the video card is one of the most expensive parts of rendering. So you don't want to, if you're rendering a checkerboard, you don't want to render a black square and then a white square and a black square and a white square and have to keep switching states between black and white. You want to render all the black squares first and all the white squares second. The problem with rendering things twice is that when I've collected all the buildings and rendered them all to the left eye, and then the grass and rendered it, and then the track and then rendered it, now I have to go to the right eye and do the same thing. Now I'm thrashing. I'm loading these things a second time. I'm loading these things the second time, okay? And that's going to really choke you out. So what we have to do is reorganize our pipeline so that we load the grass and then draw the left eye and the right eye. Load the buildings and then draw the left eye and the right eye. Load the sky and draw the left eye and the right eye. Okay, and this means a reworking of our normal graphics pipeline so that we can have multiple render targets and multiple cameras. Now fundamentally, this problem is not so bad because the hardware is going to support us. The easiest way to draw two things, to draw something twice, is to put another video card in the system. All right, and video cards that are going to advertise themselves as being VR ready are going to have dual or 4, like just like you have 8 cores in your computer nowadays, you'll have 2 cores on your video card designed for this. And at software level, all we have to do is submit a binocular camera and a scene, and it'll do it for us. So this is a problem that'll probably be solved in hardware. But right now, we do it in software. And what most teams do when they first start with this is they naively just draw the right eye and then draw the left eye and see how bad it is. And they find out how bad it is, and then they have to go back to the drawing board and reorganize how they do things. Okay, so not such a tough problem. Little bit tougher problem. You have to draw the future. Okay, when you're playing Call of Duty or I just got into Witcher 3. When you're playing Witcher 3 or whatever, you move your thumb and the camera moves or the character moves on the screen, and there's lag between the time that your hand moves and the time that you get a response on the screen. Okay. Because of your imagination barrier, this doesn't matter to you. Your body fully accepts very significant lag. I mean, it can actually be upwards of 100 milliseconds before you really start to, and then you'll just think it's kind of sluggish. You won't get nauseous. You won't, it won't really bother you on like some deep level. It'll just feel like, oh, this is kind of sluggish, right? Like a car that doesn't move very well or whatever. We're used to the idea of there being lag between control and a system, right? It's just, if you drive a car, if you ride a bike, whatever you do, there's some kind of lag between your decision to move, to take an action, and that action occurring. And so we're just used to it. We're used to operating, even riding a horse, there's a huge amount of lag between telling a horse to do something and the horse doing it, right? Once you're in VR, again, your brain no longer fundamentally accepts that it's interacting with a system. It thinks it's in an environment, and it expects that environment to react realistically. And if I'm looking at my hands and I'm turning my head, and as I turn, the scene is lagging. even by the smallest fraction of the way it lags in a normal video game, you're going to notice it, and it's going to make you sick. It's going to feel like this world isn't responding to my head movements the way I want it to. Okay, so what we have to do is we have to compensate for this latency with a predictive system, right? So we've taken our input, we've sent it to the game engine, it's going to write to the display, it's going to do a bunch of swapping. This whole pipe here, this is going to be 20, 30 milliseconds between the time that you've made the move and the time you see the screen. Might even be 100 milliseconds. That's just not going to work if you're doing it with your head, right? And so what we do is we say, okay, I'm not going to render the world from the point of view of where you're looking right now, or when I got the message. I'm going to predict where you're going to be, right? Or in fact, where you are right now, right? Or where you might be in 10 milliseconds. Based on your momentum, right? I make a prediction and say, okay, you're turning this way, so I'm going to draw it from this point of view. So by the time the image gets to your screen, you're facing in that direction, okay? Now the good news is this works pretty well, right? It doesn't require re-architecting whole systems. All it requires you to do is say, where is the camera? How is it moving? Move it a little bit ahead. We do this in network gaming all the time, Dead Reckoning, where we say, okay, you're moving along this way. I haven't received a message for you in a while. I bet you're here. I'll just put you here. Oh, you turned? Okay, I'll just snap you over there. And that's how we do it, right? The bad news is, of course, it's not 100% reliable. If I'm moving my head around quickly, right, then the system, and jerking, and stopping and starting a lot, then the prediction system gets it wrong. The good news about that, though, is that the more you do that, the more you're sending noisy signal to the system, the more you're shaking your head around, your brain doesn't expect to have a consistent field of view anyway. Okay, so the more accurate the more necessary this is, the more accurate it is, because it's when your head is moving smoothly and you're changing direction smoothly that you really notice lag, because you have a consistent field of view and your brain is processing it. Quickly it's not. Okay, so the more necessary it is, the better it is. The worse performing it is, the less necessary it is, right? And so you just live with that. And you can even cut it off completely. You say, look, I'm getting such a noisy signal, I'm not even going to try to predict. And your brain will be mostly okay with that. All right. So again, not a huge problem, but it requires us to do a little bit of math before setting up our pipeline. As a technical issue, it requires us to really understand the performance of our rendering system. So we really have to know how long a frame is going to take to get to the screen. Okay, and this is where hardware tools get into it, and that's not my this is how you do this kind of analysis. This has never really been my strong suit in life. I'm a gameplay programmer, but by and large what you have are these tools that tell you when a vertical sync is coming on each of your eyes, and making sure that you're loading the pipe so that it's being processed during the VSync period while we're flipping buffers. The other buffer is being processed. How many milliseconds each of these things is going to take, and you can see here we have about a 50 millisecond frame happening, or 22 millisecond frame, 2 frames coming in at 50 or whatever it is, and you just really have to know how that traffic is working, because if you're off by a little bit, then your predictive system is off by a little bit, and your users start to puke, right? So fortunately, again, this is something where it's like the specialized guys whose life is dedicated to this kind of thing give you a driver, and you give them the vectors that they say they want, and hopefully the system works, right? Okay. All right, so the last couple of things that you have to do, this is where it actually gets really painful. So with everything else I've just described, we don't have to fundamentally rework the entire way that we think about how we model the world. We have to predict where your head's going to turn. We have to draw things twice. We already know how to draw them once. We have to, we have to set up a pipeline that can do material sorting across 2 buffers instead of 1. That's not, well, it might be rocket science, but it's not difficult rocket science. The last area where we have to improve ourselves a bit is in the rendering of details in the world. Okay, so over the last 25 years that we've been doing this, we've taken advantage of pretty much like I said, every trick that movies and TV have come up with, as well as a bunch of our own tricks for fooling your eye while reducing our production costs. And not just our money, which is important to us, but actually the budget that we care about is the bandwidth between the processor and the video card. We got to get you a frame every 30 times a second, okay, and we cannot afford to model the entire world down to the finest detail with highly precise geometry. We have to produce a series of optical illusions that give you a sense of a richly textured world. Okay, and the two that I want to talk about are going to be bump mapping and mip mapping. So first, bump mapping. So with a textured object like this is a sphere with like a bumpy rock texture on it, right? What you would normally do is you model a sphere with a series of polygons. It's going to be pretty smooth, and you can a couple hundred will do you here, right? But if you wanted to model every little nook and valley, you'd have to build geometry for all of them. So instead of doing that, what we do is we take a texture, which is sort of shows the different little elevations of things and places where it's rubbed off or slightly different or whatever. And we create, and a texture map is a 2D bit map, right? Where every pixel is a color represented by 3 values, typically red, green, and blue floating point values, right? And that creates an image that gets wrapped around your object. Okay, now if I want that image to feel like it has nooks and crannies, like the dimples on a golf ball or the stitches on a baseball or something like that, I make a secondary texture that's called a bump map. Okay, and from this, and the bump map is dark where things are low and light where things are high. It's a displacement map, right? Okay, and from this bump map I derive what's called a normal map. Right, and a normal map is a regular texture, just like a colored texture map, where instead of encoding color, we use the red, green, and blue channels to encode the dimensions of a vector describing what the normal looks like at that corresponding point in the main color texture. Okay, and that normal can be used in conjunction with a lighting system to create differential shadows on the thing, so that when you rotate it or move it with respect to a light, you see the shadows move and shift as though there were little nooks and crannies there. And it's a complete optical illusion. What's not really clear on this slide, I don't know if you can see it, is that this is completely smooth in the border around it, and this is bumpy. The bump map can create a little bit of displacement for you. Okay, but just a normal bump map without that displacement will create the shadow effect. All right, and rendering with the actual displacement map, where you actually see the little cuts and bumps, on the edge, that's very expensive. Whereas rendering smoothly and just having the shadows fool your eye, that's a lot cheaper. Okay, so we rely on this all the time, right? Because when you're playing a video game, it doesn't really matter to you that object is actually flat, but as you move it, just the shadows make it look like it's not flat, because it's never that close to your face. Everything in a video game is always off in a distance. You don't need a lot of parallax and depth perception on local objects. You can notice it if somebody points it out to you, it's okay, but it doesn't bother you, again, because of the imagination barrier. It says, okay, I get that that's a flat object with a trick of light, but I don't care. Okay. By the way, if you Google for bump map, you'll see a sea of blue, right? Does anybody know why that is? Why bump maps are typically blue? Or normal maps, rather? The reason a normal map is typically bluish is because the normal off a surface is almost always pointing up. So the third dimension is almost always positive. And a normal map is a bitmap, a graphical bitmap with red, green, and blue representing X, Y, and Z. And if Z is always positive and it's usually higher than 0.5, that means blue is going to dominate the color space. There are, just as an aside, there are some other encoding schemes that because a normal naive normal map rejects about 50% of the resolution of the system, right? Because you never have negative blues. And there are encoding schemes that will use the whole range of color, but they're more expensive for the cards to process, whereas this is just a direct linear operation. So yeah, so if you Google for normal map, you'll see all these little blue, and that's why they're blue. Okay. So We handle bump mapping by being very careful about what we allow to get close to your face, making sure that we have managed level of detail, just biting the bullet and using displacement maps, creating higher textures or whatever, or having more and more smooth materials. I think we'll start to notice in video games, in VR games, there's going to be a lot of environments that feel like the inside of the Enterprise, rather than like, you know, Gollum's cave or something like that. And the reason will be that smooth textures that don't have a lot of bumps on them will just look better. Okay. So another area of detail that you have to deal with is aliasing, right? When you have a highly noisy texture like this, or it's very regular, but where it's very high frequency, I should say, where there's lots of change-ups between sections. When a texture gets pushed into the distance, you have these sampling problems, okay? Where the system, if it just naively samples, if it just throws a dart into the thing and then just spaces the darts out further and further as you get further away, then the subsampling errors will create these banding effects, okay? And you might have seen this in older games. You'll see this especially, where anything that was using software rendering back in the day or whatever. And that's just an artifact of the fact that you're taking a grid and you're sampling it, you know, at various frequencies. You're not going to get a regular result out of it. Okay, and we can kind of solve this with we used to solve this with what's called anti-aliasing, right? Where we say, okay, you know, given that a chunk of the world is going to look like that, we can sort of take, for every white pixel, we can see how many black pixels are around it and take an average there and make a little gray, and that gives a little bit of an illusion of smoothness to it and just makes things look a little nicer. It's been around forever. All graphics cards now just do full screen anti-aliasing. You know, it's very basic, and it'll make this image look a little bit more like that image, where instead of this very noticeable moraining quality on the grid, you get kind of a smeary gray, right? And you guys have been I've been living in smeary gray world, you know, for a couple of decades now. And again, imagination barrier, it doesn't bother us. It's like, okay, it's probably fogged out anyway, and we notice things popping in and out as we get closer to them, but who cares? I'm just looking at a video game. When you put this on your head and see it happen as though it's in the real world, it suddenly breaks the illusion. It doesn't make you sick the same way motion does. It's not like that, but it's just jarring and looks wrong and doesn't feel right, even if it's of the same quality as you would completely accept playing it if it was on your TV screen. Okay. So we have to understand how our textures are going to, and our materials are going to scale into the distance and make them not just look good. It's like on a TV screen, this kind of thing can look good. It just doesn't look right. And now we're in an environment where things can't just be good, they also have to be right. Okay. So, as part of the way that we handle this aliasing effect, we developed something called MIP mapping, okay, which is in OpenGL, it's in Direct3D, it's been around for a million years. It says when you have a texture, like this nice quilted texture with specular Phong lighting and all that kind of stuff, and looks great up close, and it's got bump maps and normal maps. When it's off in the distance, if I just take this map at this level and send it off to the distance and tell the card to do your worst, it's going to just downsample a thing and maybe anti-alias it, like we saw on the last slide, and that's going to be it. Okay? And what you'll end up with is these subsampling errors accumulate and create this gnarly effect where you get concentrations, especially on Phong, what's called Phong lighting, which is the highlight on a piece of lighting. It'll just, you're gonna oversample the lighting and undersample the gray around it. You're gonna lose all this detail. Okay, where we really expect something that's more smooth in this transition as you zoom in and out. So what we do to solve this this issue is called MIP mapping, where when you have a texture map, so you had this quilted texture, it's at 256 by 256, let's say, okay, you make an explicit version that's 128 by 128, and another one at 64 by 64, and another one at 32 by 32. You make each level, okay, of these things, and they're hand they're each independent of each other. Okay, they can all derive from the master image. There's automatic systems for doing this, or you can just draw each one yourself. And then the video cards, when you tell it you're using a bitmap, it knows to sample not only to anti-alias this way within the texture itself, but also with another line to filter to the MIP levels above and below it, right? So if I have this object and it's at the 64 by 64 level because it's selected by size, right? So it says this polygon, that size on the screen, you want 64 by 64. But I'm going to also sample from 128 by 128 and from 32 by 32. And I'm going to blend the results of all three, weighted by how close you are to either one of those things. Okay, so this is the fundamental MIP mapping formula. And it works pretty well, and it gives us some expected glossiness and looks pretty good on our screens. The problem is, once again, put it on your face, if your MIP levels aren't completely right, your brain suddenly rejects something that it completely accepted when it was on television. Okay, because fading glossiness and detail into the distance in a way that fools the eye is really, really tricky. And the way we've been getting away with it is that we don't have to fool your eye, because you have this barrier of the screen. Now that that barrier is down, we need to do a better job of fooling the eye. So our art costs have gone up. The technology is not going to change. We're still going to be using bilinear filtering and bitmaps, but now the artists have to worry that their bitmaps have to look persuasive to a VR system instead of just decent on a TV. So that's pretty much the bulk of the talk right there. These are like the big considerations for how we're going to make VR work and look better. And as I said, I think this is fundamentally, this is going to be a process of meeting in the middle with the audience so that people will get used to the way VR is. It'll start to feel like a normal experience, the way we're used to computers today, the way we're used to movies and TV. And the technology is going to improve and improve and improve. But most fundamentally, what we as developers have to do is we have to learn how to appreciate the difference between simulating reality, creating an interesting image that people appreciate as an image, and delivering what the body and the brain is going to accept as a real reality. Okay, VR is it's not SR, it's not simulated reality, it's virtual reality. The word is virtual, right? What virtual means is indistinguishable from in an important way. And VR is, of course, completely distinguishable from reality, and I think it will be, far into the future. But it's indistinguishable on certain levels, right? And we've moved into a place where illusion, and we've made our whole career out of building different kinds of illusions, suddenly becomes less and less of a viable way to do things, and you have to truly model what's actually going to happen. The future for VR, if we get past all, we would come up with MIP mapping and aliasing technologies and predictive systems and all this kind of stuff to solve all these little problems. I'm sure things will get better and better. But where we really have to target is creating absolutely perfect photorealistic renderings of our environments. Fewer illusions, more actual light scattering, more actual what the real world would do to your eyes has to be coming off of these screens. And whether or not the social or the commercial reality of a VR helmets, whether this is a fad or the next big thing or some fundamental middle ground is met there or whatever, the technological push that's going to be required to make it work is going to benefit us for motion pictures, for video games, for everything in graphics. Because what we have done is we have kicked the crutch out from under graphics development, the crutch of illusion that we've been using for decades, and now we've made it an imperative to get to where we can really simulate the optics of the world. And I think that is going to have a benefit for us far beyond whether Oculus or Samsung managed to have a good Christmas this year or next. So thank you all for your attention, and I think I have time for a question or two if there are any.
Questions?
Yes?
So how do these technical considerations apply to things like virtual desktops and stuff like that?
Virtual desktop in the sense of...
I don't know if you've done any work on this, but in terms of, let's say you have 3 monitors, but you slap on a VR headset, you have a super monitor, right?
Right. Oh, you mean like a VR desktop or work environment. There you have, again, it's, you have 2 levels of expectation that you're fulfilling. One is the mechanical expectation of working at a computer desk, and that's very forgiving, right? Doesn't have to be truly real. And the other is the limbic and basic body expectation that anything that's simulating reality is going to do so in a way that doesn't trigger things that make you sick, right? So, now you have a super monitor. If you're spending a good deal of your time looking at that monitor, as long as we're tracking your head movement in such a way that doesn't make you sick, the actual image that's coming to you is a screen. So now you have, I hadn't really thought, this is a very good question, I like this, I'm going to put it into the talk later on. Now you have a virtual imagination barrier. That's not between your eye and the screen, it's between the screen, it's on the VR system itself, where you think you're in a reality looking at a screen or watching a movie, and the fact that there's a virtual screen in there means that you're going to be forgiving of what's on the virtual screen, as long as the environment itself comes across correctly, so that when you're looking at your super desktop, if there's anything that's supposed to be around it, that looks okay. Now, if the super desktop is a full, to us it's a sphere, to them it's a flat circle kind of experience, right? Then the fact that it's intended to be entirely an artificial environment that's not supposed to be real means that pretty much you're down to the motion tracking issue. That's the number one thing that there's no way around that one. But like MIP maps and sparkly things and all that other kind of stuff, you'll be more forgiving because you're expecting that you're psychologically expecting that you're looking at a fake thing. So, yes.
Aliasing comes from having a uniform sampling period.
Right.
And one way to get rid of it is to randomize the sampling. Has anybody played with that?
Well, anti-aliasing it's not really randomization, right? It compensates for it. Randomized sampling, yes, but the problem with it for something like this is that you don't want to get a sparkle effect. So the randomness has to be consistent, and then it has to scale, right? And then you end up with the same problem again, where okay, yeah, you're not as square and blocky anymore, but you're also not disappearing into the environment, and when I move, you kind of do this and you swim, right? So, and the other issue that we have is that aliasing is supported on the hardware, right? So anti-aliasing is on the hardware. So you can do a lot of work to try and do randomized sampling inside of your textures, but fundamentally you're submitting it to a card, and the card's going to anti-alias on the screen for you. So that's kind of the best we have right now. Yes.
So I tried on a virtual reality headset, and everything was blurry because I have astigmatism and I can't really focus on things up close. Are there going to be considerations in the future for people who can't see things up close?
Well, sure. So that's another. I mean, I should make another talk called biophysical considerations of VR. Fundamentally, we do have a problem. Not everybody has very good binocular vision. Right, astigmatism, lazy eye, a missing eye, anything like that. I know a lot of people who can't do 3D movies, right? It just doesn't work for them, right? And so, basically, we're going to be in that same kind of path that 3D movies are. And 3D movies nowadays are fantastic compared to the 50s, where it was like the old red-blue technology, or the 80s with the polarized technology. This is great, but some people just can't do it. For astigmatism, most fundamentally, we need to be able to. You need to be able to focus close up. Some lens needs to be able to correct, right? And so, if there is a possibility of a corrective lens that will allow you to focus close up, then yes. If there's no such possibility, then play AR games instead of VR games, I guess would be the thing. Yeah. Yes.
Since you brought up 3D movies, I got to ask, do you think VR movies are going to be something we look at in the future with this kind of technology?
Yeah, so there's one bit of this that I kind of left out, which is what I consider to be the virtuous circle, which is what I think will make VR be a relatively successful technology, even if I am skeptical of its full market potential, is that we have artists developing the content for VR that's intended for VR. Whereas previous VR experiences were about, let's take Doom and slap it on your face. Now it's like, no, let's figure it out. Including things like you don't have body modeling very well right now, and hand modeling is just coming along. So we have these games where the premise is you're paralyzed in a wheelchair. You're being moved from place to place because nobody has a walking system in their house, and because you're not going to run up the side of a building like Neo or whatever, right? So we'll paralyze you, and then we can put you on a rail. Lots of things. A lot of these experiences are on rails. The most compelling VR experiences I've had, they're not movies, but they are very, very linear railed systems that do this. The other major technology that indicates that this is going to, that this thing is going to have legs is that they're making virtual reality porn, right? So the porn industry has hit this thing. They have their 2 cameras set up, and it's on the device. And once porn comes to your house, you're going to be okay for a while, right? So I think we're going to see definitely linear home entertainment. Some of it will be movies. I think a lot of it is going to be sort of more linear virtual games that are kind of like the old adventure games where you're going from one fixed set piece to another. And there'll be, perhaps for the first time, a real merger of linear entertainment with interactive entertainment. Will we be seeing like major theater experiences that are VR? I bet you before movies it's going to be concerts and sports, right? Because you have the content there. One of the projects I worked on for a little bit was a virtual skybox where you would watch a real soccer game from the point of view of real cameras. It's being rendered onto this field, and you're in this skybox environment. And it was kind of cool, kind of social, and but not necessarily the best way to watch a sports game. And so I think that there might be more of an element of social interaction, like we're all on a roller, like the studios down in LA where you got a roller coaster through Jurassic Park kind of thing, right? That you want to enhance the group experience more when you've made it this VR thing, so that we're all looking around different places and we're all kind of on this car. So short answer is yeah, I think we will, but the longer answer is I don't think it's going to be like you're in Star Wars. It's going to be a series of different kinds of gamic and like sportsy and concerty experiences at first. One more?
Another question. I think I asked you this last time. Is anybody taking into effect the input from the vestibular system on the eye motion? Because the semicircular canals tend to keep your eyes stationary to move your head.
Right.
And there's a lag, and your eyes do a saccadic movement.
Yes, you tend to keep your eyes fixed and then they jerk around.
And that comes from the vestibular system.
Mm-hmm. So that speaks to what I was talking about with the predictive movement. The best way to screw around with predictive movement is to fix your eye on the distance and move your head like this. Because then the system is shaken around, but your eye is fixed in one place, so your field of view is consistent. So I don't know about actually manipulating the vestibular system, but fundamentally it's about the faster your eye is moving, the less your brain expects a consistent field of vision, the more forgiving it is of things being incorrect, right? So your eyes tend to fix and move and fix and move and fix and move. We're not yet doing eye tracking. That is something that will come for this, because I don't think we can fundamentally solve the head moving problem without eye tracking. We obviously can't control the way your eyes move, right? But we can start to respond to it, and I think third or fourth generation, you'll see things that understand where you are looking, and that'll be a major improvement on the predictive head movement. Yeah.
Russians, thank you so much.
Thank you.